We started our section on capacitors by saying they were a useful device because we use them to store energy in circuits. Remember, we showed that 1 farad was equal to a coulomb squared per joule, and we know that electric potential energy is stored in the electric field between the plates of a capacitor. Let's start to look at how that works. So let's think about a case where we have a capacitor connected to a battery. We know that overall a net charge, capital Q, is going to flow, but let's think about what's happening somewhere in the middle of the charging process. So at some point during that charging process, there is an amount of charge on the positive plate and an amount of negative charge on the negative plate. So at some point during the process, the plates have charge plus and minus Q. And this charge is between 0 and the total amount of charge that eventually will be transferred. So next, let's think about what's happening inside that battery. In the process of the charging, a small amount of charge is moving towards the positive terminal of the battery. And the reason it's moving that way is because of the chemical reaction within the battery itself. So the chemical process inside the battery does some work and it moves that charge towards the positive terminal. So that's what's going on inside. So a little bit of charge, dQ, moves towards the positive terminal, of the battery because work was done by the chemical reaction inside the battery. So if we've done work on a little bit of charge, its potential energy is going to increase. And we know potential energy is charge times the change in potential. So the electric potential energy of the little charge dQ is going to increase by a little bit, which we'll call du. And we'll say du is equal to the little bit of charge that's moving, dq, times the potential it moves through. So from the negative to the positive, it'll move through a potential of delta V. What are we going to put in for delta V? Well, something we know about the relationship between charge and potential is capacitance. We know capacitance equals charge over potential. So that tells us potential is going to be charge over capacitance. Let's fill that in for our delta V. Equals dq times q. The charge on our plates now is q at this point in the process, divided by c, which is the capacitance, which is a property of the physical properties of the plate. So for my result, I've got q times dq over c for a little bit of the change of electric potential energy in that charge. If I want to find the total electric potential energy U, I just have to add up all the little bits. So my total energy is U, which is the sum of all of our little bits of energy. And remember, when we're adding up a bunch of small things, that's an integral. So we're doing the integral of Q times dQ over C. We're adding up over all the little bits of charge. So the charge starts with nothing, and it stops when we get to all of the charge, capital Q. I can take my constant 1 over C out front, integral of 0 to Q, Q dQ. The integral of q dq is q squared over 2. I don't drop my c there. Then that's going to be evaluated at q and 0, which is going to give me q squared over 2c minus 0 squared over 2c. So that term is 0. And let's see what we can do here. Well, we remember that that net charge Q is the change in potential times the capacitance. So charge is capacitance times potential. I can fill that in there. So I've got capacitance times potential squared over 2c. I might notice here when I square both these terms, I'll have a c squared on top and a c on bottom. So that's going to leave me with my half. C squared over c is c, and then I've got delta v squared. This is kind of a neat result. This looks a lot like U equals a half kx squared for a spring. If we stretch out a spring, the energy is stored until we let it go, and then it starts a mass moving. For this guy, we store the energy in a field until we release it and let it go, and then the charges start moving, which means current flows. And that's what we saw in that little PhET simulation when the light bulb started to light up as soon as we connected the capacitor. All of the energy that was in the stored potential energy moved into kinetic energy of that charge flowing around. The charge flowing was a current which lit up the light bulb. Okay, so last, let's just write down our result, because this is important for us to know. Potential energy of a system with a capacitor is q squared over 2c, and it's also equal to 1/2 times c times delta v squared. So these are ways we're going to calculate the net potential energy stored in a capacitor. Let's do a couple of examples. We'll do one that's a really straightforward plug and chug, and then we'll do one that has a little bit more putting all the things together in it. So the first one, energy storage in a capacitor. How much energy is stored in a 220 microfarad capacitor that has been charged to 330 volts? So let's just write down what we know. The capacitance is 220 microfarads. That's times 10 to the minus 6 farads. It's been charged to 330 volts. That's delta V. So if we want to know how much charge is stored, let's call that part A. We know that the stored energy is 1/2 times C times delta V squared. So we've got 1/2 times 220 times 10 to the minus 6 times 330 volts squared equals 12 joules. And then the second part, what is the average power dissipation? So what is the energy over time if the capacitor is discharged in 1 millisecond? So now we're saying that the energy is going to be discharged over a time of 1 millisecond. 1 times 10 to the minus 3 seconds. So then we'll remember that power is change in energy over change in time. The change in energy is our capacitor discharging, it's 12 joules. Divide that by the time it takes, which is our 1 millisecond, and that gives us a power of 12,000 watts. That is a lot of power in a camera battery. So kind of how this works is that our camera battery charges up the capacitor. Kind of takes a long time because there's a lot of energy, but then it's released pretty quickly. It's why you can't get two flashes right on top of each other in general. Okay, now let's do our next example, which has got an environmental context. And let's ask, what about the capacitance of a thundercloud? So if we have a thundercloud up in the air, I think I'll draw that in black because they do tend to be pretty gray. So we've got a big cloud up in the air. It's drifting 3 kilometers above the Earth's surface. So let's get the Earth in there. So there's our Earth's surface. The distance between those two guys is 3 kilometers or 3,000 meters. It contains 20 coulombs of negative charge. So the charge on our cloud, Q, equals minus 20 coulombs. That is an awful lot of charge. Assuming that the charge center has a radius of 1 kilometer, so our cloud has a radius of 1 kilometer, that implies that it's roughly spherical, so R is 1,000 meters. And we're going to model the charge center, so we're going to model our cloud and the Earth's surface as parallel plates. Okay, this is telling us that our cloud and our Earth act like a capacitor. There's going to be an electric field between those two guys and a potential difference across them. That's kind of an interesting idea. But we know that that's true because we get lightning strikes all the time, and lightning is what happens when that electric field gets so big that it causes a breakdown of the air and current actually flows through the air. That's called a dielectric breakdown. So this is more or less what's happening as we're approaching a thunderstorm, a lightning storm. So the first thing we're going to try and find, what is the capacitance of the system? So we know capacitance depends on the physical properties of the system. Let's write down that relationship. Part A. Capacitance is equal to epsilon naught times A over D. So let's put in our epsilon naught, 8.85 times 10 to the minus 12 farads per meter, times the area. We're approximating our cloud as a circle, so it's going to be pi times r squared. Okay, I had to squeeze a bit. That's 1,000 meters squared. And then we divide that by the plate separation, which is 3,000 meters. What we get for our capacitance then is 9.27 times 10 to the minus 9 farads. Okay, so that's the capacitance of our system. How about the potential difference between the charge and the ground? So let's find delta V next. So to find our potential difference, we remember that C is our charge over our delta V. That tells us that delta V is Q over C. The amount of charge is 20 coulombs divided by the capacitance. That gives us a potential difference between the charge and the ground of 2.16 times 10 to the 9 volts. That is an enormous potential. That's really huge. Okay, part C, the average strength of the electric field between the cloud and the ground. So if we know the potential and the distance, we can find the electric field. So part C, we know that electric field strength is change in potential over distance. The change in potential we just found. The distance is the plate separation, 3,000 meters. That gives us an electric field strength of 7.19 times 10 to the 5 volts per meter. This is really close to lightning. We get dielectric breakdown when lightning happens. The current can travel through the air at approximately 3 kilovolts per millimeter, or 3 times 10 to the 6 volts per meter. So if this were happening outside, you'd be getting that prickly feeling that tells you that lightning is on the way. Last, let's calculate the electric energy stored in our system. So the electric energy stored in our system, we'll say that our electric potential energy U is equal to 1/2 times our charge times the potential difference. Let's put all these guys in. 1/2 times 20 coulombs times the potential difference of 2.16 times 10 to the 9 volts. That gives us 2.16 times 10 to the 10 joules. Now, when I calculated this, I really needed to put it in a little bit of context. So I went on to Newfoundland Hydro's website. That's the power generation company for our province of Newfoundland. So according to Newfoundland Hydro, the average power consumption for 1 month of Newfoundlanders, average monthly power, is equal to about 1,300 kilowatt hours. I also checked on the BC website. Theirs is 900 kilowatt hours, so they do better than we do at power consumption. But at any rate, 1300 kilowatt hours, so 1300 kilowatts is 1300 times 1000 watts. An hour is 3600 seconds. So you can do a conversion to show that this is equal to 4.68 times 10 to the 9 joules. So the energy stored in this system of the cloud to ground is about 10 times as much as average Newfoundlanders use power in a month. So that's about 10 times the energy that Newfoundlanders would use in about a year. I find that kind of neat in context.